Thank you, Mr. Chairman.
You're welcome.
Okay. Good afternoon, ladies and gentlemen. This work was carried out with the collaboration with NAV and Interpool Center. Trends in genetic variance benefit those pools which are coming from the populations and year classes with increased genetic variance, and this leads to suboptimal selection decisions. Thus, national evaluation centers and Interpool Center, they need a test to detect these defects and these trends. And so far, two approaches has been proposed to estimate within-year genetic variances. First, IBOM3 developed by Interpool, and the second one is full model sampling, which was developed by Lidauer et al. Even though we have two different methods to estimate these within-year genetic variances, no test has been implemented yet. The aims of this research project were to dissect the behavior of those two methods on cows and bulls by performing simulation study. And these results were reported last year in Stavanger. And another aim was to develop the test to validate consistency of Mendelian sampling variance in national evaluation models. And I'm reporting these results now. Tentative validation procedure. Within-year genetic variance is estimated according to Fix et al. Here in the equation, QA is the number of animals in year, DK is the inverse of the proportion of genetic variance not explained by the known parents. M squared is the squared estimated Mendelian sampling term for an animal. And PEV is the prediction error variance of that Mendelian sampling term. And it has been approximated following the method published by Fix et al. And it utilizes only variance ratio, not genetic overall or population-wide genetic variance. The data used for testing, this test can be performed either for cows or bulls, and the time period of 12 most recent years is going to be utilized. And the number of animals with observations in the most recent year class must comprise at least 50% of the average yearly size in that testing period. And then we need those EBVs and reliabilities for animals and their parents to calculate the Mendelian sampling terms and prediction error variance of those terms. Then we are going to fit a weighted regression model on estimates of within-year genetic variances to test the possible trend. And a number of animals in year classes are used as weights. We are going to define empirical 95% confidence interval by bootstrapping data with 1,000 tree sampling within years. So we obtain 1,000 terms for beta 0 and beta 1 terms. An empirical confidence interval for a trend is expressed as a percentage change in genetic variance. Possible outliers that do not fit the model are identified by also collecting residuals from those bootstrapping steps. And then we are defining 95% confidence interval for the residuals. And then we are checking is the expected value of 0 lying inside that confidence interval. And if it's outside, this kind of data sample is considered as an outlier. This p-value has been only tested for small populations, so we still have to test this way of defining outliers for larger ones. And then the tolerated level of bias. For very large populations like cow populations, test has a power to detect very small deviations from 0, which have no practical influence. So we really need a tolerated level of bias, which tested population must exceed before the problems are reported. And the validation of this validation method. The data comprise Danish Holstein cows from 2,000 herds, including almost 800,000 cows. And test day observations were replaced by simulated ones, and alternative scenarios were generated for variance bias. Data were analyzed to yield 305-day EBVs for cows and bulls. And then we also collected a subsample mimicking small bull populations. And the average number of animals in year classes were 45,327. We had two different testing scenarios. Scenario A served as a control with a homogeneous variance structure. For scenario B, a yearly trend of 2% in phenotypic variance was generated. Then EBVs were calculated with heterogeneous variance adjustment or without that adjustment. We analyzed 20 replicates in each testing scheme for its three populations. And the within-year genetic variances were also estimated under full model sampling approach. Then to the results and discussion. Estimation of within-year genetic variances. Here you can see two figures, on the left-hand side for bulls and on the right-hand side for cows. And these are estimates average over 20 replicates from scenario P without HV. And if you first look at the figure for bulls, you can see that the within-year genetic variances are very similar from IB4 and full model sampling. The dots with red one are from the full model sampling and with turquoise from IB4. So for the bulls, the results are in a very good accordance. But then when we look at the figure for cows, it doesn't look so nice as for bulls. The overall level of the estimates from IB4 is on a higher level, and there are notable peaks in the most extreme year classes. And then we wanted to study what is behind those peaks, and we noticed that majority of the cows in those extreme year classes were cows with very low reliability values, under 0.50. And we removed all those cows with low reliability values, and both peaks disappeared, and the overall estimates of genetic variances came closer to those obtained under full model sampling approach. So this quality of estimation of genetic variance relates to value of approximated prediction error variance, which is further associated with the level of approximated reliabilities. So we must carefully restrict the data used for testing, but we cannot restrict it based on reliability values, causing a selection bias. Then to the sample size. Populations such as 1 and 2 can be utilized in testing, but then use of populations such as population 3 with average yearly size of under 20 might be difficult because large sampling error. This figure is representing one small replicate on the scenario B without HV correction. So basically there should be an increase in trend, but you cannot see it. And there is a notable fluctuation in the estimates of genetic variance. Tentative statistical test. For both populations 1 and 2, generated and not adjusted bias was detected by the test in all cases. Applying heterogeneous variance adjustment resulted in slight decrease in trend, indicating that this HV adjustment overcorrected bias. And it was on average minus 0.16%, and it was detected as statistically significant deviation from zero in cow data replicates which had large year classes. But only 1 out of 20 data replicates in bulls deviated statistically significantly from zero. So these results illustrate a need to define a level of bias that has no practical influence and can be tolerated. Here you can see the same results as the figure. On the upper level, there are cow and bull replicates without HV adjustment, with the overall trend in 2%. And on the lower level, you can see results for the cows and bulls when we have carried out the HV adjustment. And all those green dots, they are for the bulls, and the deviation from zero were non-significant in all other cases, but well, I have no pointer, but there was one replicate with a significant deviation. But then if you look at those red dots, they are from cow replicates, and they all deviated statistically significantly from zero, even though they were very close to zero trend. This slide illustrates the detection of outliers. So again, this is a small pool data replicate under scenario B without HV adjustment. And all these circled cases can be considered as outliers when we bootstrapped residuals and fitted a confidence interval and tested is zero lying inside the confidence interval or not. Then to the conclusions. The proposed procedure consists of the following steps. First, we must estimate within genetic variance by utilizing Mendelian sampling terms and prediction error variance of those terms. We fit the regression model on variances with yearly number of animals used as weights. Third, we identify the possible outliers. And fourth, we define 95% empirical confidence interval for a trend. And country or evaluation center is noted for problems if that trend deviates significantly from zero and exceeds tolerated level of bias. Then, estimates of within-year genetic variances from IB4 and full model sampling were in a good agreement for bulls, but for cows, IB4 is less robust with low reliability values. So data used for testing should be carefully defined. And use of populations such as population 3 might be difficult and should be avoided. Thank you.